A fission reaction involves the splitting of a heavy nucleus to produce lighter nuclei and 2 or 3 neutrons, which can be used to split more heavy nuclei, causing a chain reaction to occur. During fission, not only are neutrons emitted, but a small amount of mass is converted to energy. At first glance, the loss of mass seems to contradict our concept that matter can neither be created nor destroyed. However, properly expressed, the law states that the total amount of matter and energy must be conserved. The fission process begins with the capture of a neutron by a heavy nuclei. The nucleus produced by the neutron capture is unstable and immediately splits into 2 medium-sized nuclei, releasing neutrons and energy. 2 examples of fission reactions are shown here, in which uranium-235 is bombarded by a neutron to produce 2 medium-sized nuclei and some neutrons. During fission, a small amount of matter is converted into energy. For example, during this fission reaction, the total mass of the uranium-235 and neutron before fission is greater than the total mass of the cesium, rubidium, and 2 neutrons after the fission reaction. The difference in mass is called the mass defect. This mass is converted to energy during fission. The relationship between mass and energy is expressed by Einstein's famous equation E equals mc squared, where E equals the energy released, m equals the mass difference or mass defect, and c equals the speed of light, which is 3.00 times 10 to the 8 meters per second. Because the speed of light is such a large number, you can see that the conversion of a small amount of matter produces a very large amount of energy. This slide compares the risks and benefits of fission reactions. If used appropriately, nuclear power from fission has the potential to reduce dependency on the continuously depleting fossil fuels. This reduction would decrease the amount of gas that contributes to global warming as well. However, the gravest concerns associated with nuclear power from fission are the release of radiation into the environment, a nuclear meltdown or accident, or and the storage of radioactive waste. Fusion occurs when a small nuclei combine into a larger nuclei. The most common example of fusion occurs in the Sun, where hydrogen nuclei react to produce the helium nuclei and a tremendous amount of energy. In this reaction, the isotopes of hydrogen called deuterium and tritium join together to produce the larger helium, 1 neutron, and a huge amount of energy. While fusion produces the energy from the Sun, it is not yet available to produce energy here on Earth. Extremely high temperatures and pressure are required to allow the positive charged nuclei to join together. Researchers have not yet created a fusion reaction that can produce more energy than is needed to sustain that high temperature and pressure. However, fusion offers important advantages: no carbon emissions, no air pollution, and an unlimited supply of fuel, because hydrogen can be easily extracted from water.